copy number changes can occur due to DNA replication. That can definitely occur. We can have unequal sister chromatin exchange, leading to differences in copy numbers of different repeats. That's the third one. And epigenetics. So in terms of methylations occurring that can travel through, maybe in some cases in one twin there's more methylation of one gene than in the other twin. All these things are going to be occurring, and that's why I have it in quotes, where it's the same DNA in the beginning technically, but throughout the lifetime as they develop, slight variations will be occurring, even with monozygotic twins. So once again, he has the same slides like 7 times, so make sure you understand this, feel comfortable with it. Once again, quantitative traits as opposed to a dichotomous trait, where it's just simple Mendelian genetics, big A, little a, and just that gene can affect the phenotype. Once again, the haplotype blocks, where right down here in block 4, those are 4 of the possible haplotype blocks that are occurring at this location. So at this overall block, I have either the orange, purple, green, or red. And within there, if I know for sure that a person has a C and a G right here, then I know what the other ones are going to be. And I know what those alleles are going to be within those genes. So, goes back to the question earlier, we're talking about, well, how do we said it's, I keep saying, oh, well, we sequence the SNPs or the VNTRs and we just do it. We haven't really talked about how the sequencing occurs for them. What we do is we're basically going to do DNA microarrays. So, once again, I think this is from the second exam, we need to be comfortable with RNA microarrays. You don't need to go back over the lecture, but what's the main gist of RNA microarrays? What do? We take all of the RNA, I convert it into what? cDNA. I add the probe, I then throw it on the chip. What's on my chip? Oligonucleotides that are we have made those, right? And the sequence on there is I'm going to make that sequence to bind to that cDNA. So I'm making that bind to this, and depending on the number of times, how many transcripts we have, they all bind onto the chip, they get a brighter color, I can then say, okay, I have this amount of this transcript. So that's the whole idea for RNA microarrays. Now we're doing DNA microarrays. Same idea, but one less step. We already have DNA to begin with. So we don't have to convert it to cDNA, it already is DNA. So in this case, what are we doing? And there's no fluorescent probe. It's a different color thing we're talking about. So, once again, between all of us in this room, if it's not a SNP or a VNTR or an allele, assuming no mutations, we all have the same exact sequence. What's different are the SNPs, right? The VNTRs. So let's use SNPs as the example. For DNA microarrays, I order a chip. The chip will still have oligonucleotides on it, but guess what these bind to? The conserved sequences in all of us that are basically the sequences of DNA right next to a SNP. That's all we're doing. So I make an oligonucleotide, have it on my chip. So once again, the chip's really big. We'll focus on just one area, one unique little block, and that's this oligonucleotide right here. This oligonucleotide at this one location is going to be a unique RS number. What is the RS number? What is that? What's that?
SNP.
That's a SNP. RS stands for RS, and a long number is a SNP. Make sure you're comfortable with that. So we've designed this because I know that this sequence is the same in every single person. What's different is whatever should go right there. This top one, this is not here. That is where the SNP is, and I have no idea what the SNP is going to be. I have an idea it can either be one of the 4 bases, right? Or sometimes it's more or less than the 4. But let's say this is the SNP. So what I do is I take all the DNA, I take the person's DNA, I break it up, I then throw it on this chip. I'm going to throw the DNA on the chip, and every person, will they get DNA bound to this area? Yes, because everyone has, this is a conserved sequence. Everyone has this sequence. So what's going to happen is, you're going to have this binding to that. Just like that. And this part right here, that is my SNP. However, I don't have, my nucleotide doesn't go up there. That's on purpose. Because my whole goal of doing this, I want to figure out what this is right here. So once we do this, we have it on this microarray, on this chip, and I have the DNA, your DNA I broke up, throw it on there. Now guess what I do? I now add the bases, similar to like talking about going back to massively parallel stuff. I'm now adding bases to this that are going to be color-coded. So let's say,
These are the fluorescent.
yeah, these would be fluorescent nucleotides. We're now, let's say, this brown one is an A, so what had to be here? A T. So that tells me, oh, an A binds to the T here. So therefore, at this person, they have the T SNP right there. And what's the point of doing this? I've now identified what? The haplotype block. So, if I do this, and let's say everyone with the disease state has this SNP. Whereas the general population that are not affected, they have an A, or they have a C right here. And everyone with the T, they have the disease. So that tells me, wherever this full block is, let's assume that the block is like something that's like this. Within this block somewhere, that is a good candidate for the gene responsible for that disease. So that's all we're doing. So it's a combination of the RNA microarrays plus a little bit of that massively parallel sequencing. We're doing them both sort of simultaneously. Once again, that's what it is for the microarrays. Now we're doing it here. Once again, here are the RS values. Those are the SNPs that we're going to be focusing on. Keep in mind, when we are adding that fluorescently tagged nucleotide, we're adding it to, not to the actual DNA, we're not adding it to the patient's DNA. What's it being added to? The oligonucleotide. We're building this up, not building the new, or not building the original or the source DNA. We're building up the oligonucleotide because I want to see what is this SNP right here. So on every part of this chip, I've got a different SNP, all going all the way down. And you can do it for as many SNPs as you want. We don't need to do it for all 3.1 million SNPs. At the end of this lecture, we're going to talk about how many SNPs we need to have to get a good, basically, percentage to make sure we're covering our bases. But for now, if you want to, you can get a chip that has all of the SNPs on there for every single one. So that means that you could do it for all of these SNPs in here. Every single one of SNPs in that haplotype block. But really what we do is we use one or two. Depending on other variables, then we use that. What's up?
Are you supposed to have the projector down? Or
Yes. It's the Christmas tree photo.
Wait, what's that? That might be you.